want to ask you this. Have you returned to
The COD Zombies community?
just visiting? Have you thought this through? I mean, chewed down to the bone. You got out once. You dip so much as a pinky back into this pond, you may well find something reaches out and drags you back into its depths.
Hello there, it's Acered, your favorite science guy. It's been a while since I made a video, but I've been called out of the shadows to address something I was mildly involved in. So I decided to make a video about it, and here we are. This video will be split into 3 parts. Part 1 will be about the binomial distribution, how it works in the context of the box, and why. Part 2 will be addressing my involvement in Crupp's video, particularly about the math near the beginning, and part 3 will be using Python to dive into the math of the box in general, which will be good, a bit of fun. And before we start, I want to make a few things clear about Crupp's video. As Cruppz mentioned, I was not involved in the data collecting and analyzing of the game. That was done by Cruppz and his friend. I was not involved in any of the drama that was mentioned in the video, nor do I really know what it's about because I didn't really finish the video. And I only advised on the math, and particularly what I'm going to explain in this video. Only reason I'm making this video is because it would be useful for transparency, plus educational reasons, and also Cruppz could have presented the math a bit better, but that's okay. Okay, so let's get on with part 1 of the video. So, in order to statistically analyze the box, I'm using the logic of the binomial distribution. This means that the box follows the following few statements. Independent trials, which means that each trial or box hit is independent of the others. The outcome of one box hit should not affect the outcome of another. Sampling with replacement, assuming that the gun is put back in the box after a trial is sampled. This means that the gun is always back in the box and available whenever a trial is counted, which makes the probabilities independent, which will be important for later. There's only 2 possible outcomes, so each trial can be categorized as either a success or a failure, so you either get the gun or you don't. And the constant probability of success means that the guns in the box remain the same, and that's 0.05 or 1 in 20 in our case. Discrete outcomes, which means that each trial does not have like a 0.5. It's always 1 Tegan, never 1.5 Tegans or 0.5 Tegans. So, as you see, I've made a little Google sheet, which should be linked in the description for you to download and play around with. In the first tab, I have a little demo on the binomial distribution of a gun being picked out of the box. So, this giant PNG here is the binomial formula. It shows the chance, the probability of getting X amount of successes. And this fraction here is the number of ways you can rearrange an event, or the number of ways an event can occur. P is the probability of chance of success, so 0.05 in our case. X is how many successes you're targeting, so each one of these. Q is the chance of failure, which is 1 minus P. And top right here is the number of failures, which is the total number minus the success number. So if you look here on the left, I have various values of X. And luckily Sheets has a built-in formula for the binomial distribution, so I don't need to type this horrible formula out. So for each number of X, I've just put in the corresponding probability of getting that using the total values N here and the chance of success P here. And in other words, if you translate this into kind of more human language, out of hitting the box 200 times with a chance of 0.05, 1 in 20, getting exactly 10 Tegans is 12% chance. And getting exactly 14 Tegans is 0.05% chance. So this is what this column means. Looking at these numbers is not entirely helpful. So it's better to visualize data with graphs and stuff. So here I've made a bar graph which gives us a very helpful visual representation of this data with the probability px on the y-axis and successes on the x-axis for each bar here. So from this we can clearly see the bell curve that comes with a binomial distribution, and we see that the majority of distribution lies in the middle with probabilities getting lower the tail end of this bell curve. Number 17 is much rarer than number 10, and number 4 is much rarer than number 10, 9 and 10. However, choosing just one of these values and then claiming that it's rare is a bit misleading. For example, if we look at the number 10, and as you can see, it's the most common number of successes, and it happens only 13% of the time, which is correct, but it's oddly specific to do just 10. You know, we're almost as likely to get 9 or 11. So there is one way you get around this, and that is to look at the probability of getting a specific number or better. So if we look at the number 13, for example, we'd say the probability of getting 13 or better, which is what this blue column on the right shows. So number 13 or better is 20% chance, which kind of looks like, as you can see, you can kind of imagine that 20% of the graph is contained in here. Or alternatively, if you look at the number 5 here, you can see that 97% of the chances are better than number 5. So you are 97% likely to get a game that's equal to or better than 5 hits for whatever T-gun or gun you're looking for. Okay, so hopefully I've explained the math and the numbers that are going on this page. If there's any questions, please ask in the comments. I'll try to address them, but I'd like to move on to part 2, which explains the math that was done in Cruppz's video. So, moving on to this little tab, this calculator tab at the bottom of the Sheets document. Here I explain how I got that 1 in 150,000 number for Furret's 244 Ascension game, as well as the assumptions you need to make for this. You decide if you agree with them or not. So, a trial or success is only incremented if there's a chance for it to happen. For example, if you have the T-gun in your hands, in your slots, and you hit the box, it does not count for a trial for the T-gun, because there was absolutely no chance you'd get the T-gun. Same for Gershes and those. On the topic of those, I've seen people argue that we should not count if the player doesn't pick up the doll. And I think that is kind of a non-argument, because if the dolls are rolled and the player doesn't pick them up, it still counts as a trial and a success. However, arguing if the doll should be included as a target weapon is a whole other question and issue which is not about the math, so that's up to you. Okay, so here I've created 3 columns, each one of them represents a gun, and in these boxes is the inputs that you need to do to calculate the probability of getting that, so the chance of success, the number of trials, and the number of successes, and these 2 boxes are the results of that calculation. And if you remember the blue text here, that is this. So the chance of getting this many T-guns out of this many boxes or better is this. So it's about 1 in 76. And it's the same for these 2. This is for Gersh and this is for the dolls. And also here, just because some people like seeing it in trade averages, I've put the trade averages here. So that is just number of trials divided by the number of successes. So now we have the probability of getting the 3 guns or better individually. And because they're independent events, the chance of getting 3 independent events at the same time is you multiply them together. And that's how you get the 1 in 150,000 number. And you get this number. So it's this multiplied by this multiplied by this. Hi, hello, it's Aceret from the future here, and I just want to mention that I've seen people mention that multiplying 3 decimals together will always make the final number more luckier. That is true, but it isn't an argument against this. This is just the way you calculate the probability of independent events happening at the same time. So if you think of the example of, if you use the example of a dice, and the probability of rolling a 1 is 1 in 6, but if you want to roll a 1 3 times, it's going to be 1 in 6 multiplied 3 times. So that's going to be 0.04 or something like that. Let me get the calculator. 1 divided by 6 times 1 divided by 6 times 1 divided by 6. 0.004. However, it is important to put this in context when you're comparing likelihoods appropriately. For example, if you want to compare Furred's game to another player's game, you have to make sure that you're calculating the same measure, so the same free guns. So in this case, that would be the T-gun, Gersh, and Doles. And if you don't want to compare the Doles for whatever reason, you have to make sure that you're comparing only the T-gun and the Gersh, or maybe the T-gun and the ballistic knife, or whatever you choose of the two people's games, Furret and whoever. And then that might help you put into perspective how much luckier this is compared to another game. So I don't remember exactly what it was in Crupp's video, but I think one of them was 1 in 100 versus 1 in 150,000. That's a whole different ballgame. So similarly to the complement of the CDF, which is equal to or better, I've also put the CDF here, which is equal to or worse. So the probability of getting this many T-guns or worse is 99%. The probability of getting this many Gershes or worse is 97, and those this. So this is kind of the opposite, and as you can see, it's almost about 1 in 1. It's almost all the time. And here's the same calculation when you multiply them all together. So it's a way to measure, I guess, how unlucky you are, but you can kind of infer that from the complement of the CDF as well. But I put it here for completeness. And as a sort of segue into the next part of my video, here at the bottom I've put a few plots that I've made in Python, and it kind of helps to visualize better the previous graph. So for the this is the plot of the T-gun, this is the plot of the Gersh, and this is the plot of the Doles. And as you can see, for the T-gun, it is all the purple games. So all the purple distribution is equal to or better. For the Gersh, the same, and the Doles the same. So as you can see, they're quite lucky, the three of them. So yeah, just to reiterate again, the reason this is so low is because you have 3 very lucky independent events happening at the same time. So yeah, as you can see, they are like fringe tail end probabilities, and when you multiply them together, it just becomes very lucky, because for them to happen at the same time as independent probabilities or independent events is just very lucky. Okay, so I think that clears up all I wanted to say about Crupp's video and address any things that he would have left out. If you have any questions, please put them in the comments, and I hope I've been as clear as I can, and I hope I didn't make any mistakes. If I did make mistakes, do let me know as well. But yeah, I think the next part of the video is going to be quite fun, because we get to see some interesting things about the box and things that kind of surprised me. Also, if you're super interested, this math is very similar to how they exposed Dream for cheating, and I think the video by Stand Up Maths, he's really good. He explains it really well. It's similar, very similar to the math I'm doing here. So, and if I didn't help you understand it, this guy definitely will. So go check this video out. And before anyone in the comments claims that I'm saying that Dream's luck is comparable to Furret's luck, no, that's not the case. This is just a good video for explaining the math involved, if I'm struggling to do that. Hello and welcome to the second part of the video, which is going to be about showcasing this little repo that I've made with the purpose of simulating the box and statistically analyzing the outputs of this simulation. It is publicly available, so feel free to pull this repo and mess around with it yourself. Hopefully to serve as a useful educational tool or something to play around with. Okay, as you can see by the file extension here, all of these files are written in Python. I have a little bit of a setup here, installation guide written on how to install the necessary dependencies for this repo. But if you're new to Python, I suggest that you look up a video on YouTube or a tutorial, as it's quietly available, and something like how to run Python code on my Windows 10, Windows 11 PC. But yeah. So to start off, remember the graphs I was showing for the second tab of the Sheets document? They were produced by the Binomial dist file. So once you have the repo pulled, you can open the Binomial dist file in in whatever editor you want. I use VS Code, it's just easy and I'm used to it and I do it at work, so yeah. So to use the binomial disk to make one of those graphs that you've seen in the calculator page, you scroll the way down, and here I've just made it as one function, and all you need to give is a name. You don't need to give a name, but you can put a name in, and the number of times you hit the box, the chance of success, and the marked success. Here I'm using for its numbers, 20 guns, 1 in 20, this many box hits, and this is the marked success. And once you run it, give it a sec, it will make a plot, and you can change the numbers around, so I can make it like 400 box hits and 20 as the marked success. And here, as you can see, it's like the middle value, and everything to the right is purple and everything to the left is gray. But yeah, you've already seen that in the other tab. And yeah, the bigger number you put in for the trials, the longer it's gonna take to generate, because it's doing a lot more bins. So if I give it something like 5,000, it's just gonna take a few seconds to run. It will appear here once it's done. There we go. Boom. It's because the mark number is so low. Every game is gonna be better than that. That's why it's purple here. But yeah, that's how you use this file. So feel free to play around with that. The intended use of this is to visualize the binomial distribution for a given set of trials, which I explained a bit better in the previous part of the video. And you can easily mark where you want it to calculate the equal to or better. Fun little fact, most of the code that does the math is just this line. All of this here is how to just plot the graph and make it nice and pretty. So that's funny. So that was the binomial dist file, which creates a perfect distribution from the mathematics of the binomial formula. However, since it is 2024 and we all have powerful computers at our disposal, why not create simulations of box hits which can run at many times per second, allowing you to get many simulations run in a relatively short amount of time. So for this, I have created a function which simulates a game with a given set of guns and a number of box hits, named run underscore box hits, and the box calc utils. And this is going to be used by all the following Python scripts. So the way it simulates a game with an X amount of box hits is it takes in the number of box hits you want, the gun list, and it just does a loop from 0 to the number of box hits that you have, and each time it chooses a random gun from that list, and it just counts, adds 1, increments about 1. So it just does that up until the loop reaches the amount of box hits. So if you just go in this file, scroll all the way to the bottom and input a number into here and then run it, it should print out a game with a sorted list of guns. So this gun appeared this many times and this gun appeared 104 times. And yeah, the sample gun list I have here just has the 3 important guns, and the rest I've just filled in with random letters of the alphabet because I can't be asked to look at what guns are in Ascension. But yeah, it takes the default list of Ascension. You can change that down the line. But yeah, so I just ran one game here and it showed that H appeared 134 times, P appeared 104 times, which was the least common. H was the most common, and you can see where the Tegan and Gersh and those lie. I can run it again. As you can see, Tegan was second most common. Very lucky. Nice. And yeah, this is what the rest of the code's going to be doing, just constantly running this and then taking the results many times a second. This file does contain one other function, but it's not really used by any of the other files. It's just kind of to help you visualize the order of the guns from small to big. So yeah, don't worry too much about this function. But this function is the one that's being used by all the other files. Speaking of, let's look at the box histogram.py. Here I use the run box hits to simulate a game with a inputted number of box hits, and you run this for num run times, this thing here, and using a list of guns, but the list of guns is I've told it to use the default, which is what we see in the other file. And you also give it a marked success, which creates a little dotted line at the value you want to highlight. Hello, just a quick intervention from Acer from the future here. It does matter what gun you type in here because it will look for that gun in that list. So in the list here. So make sure that the gun you select is in the list, though the distribution should be exactly the same because all the guns have the exact same weightedness. But yeah, here right now is looking for the T-gun specifically. It will act the exact same way if it's looking for the Gersh. But yeah, I just put that in. It's a feature. So the distributions you'll be seeing in the following graphs are all from the occurrences of the T-gun because it's looking specifically for the T-gun. So with a small sample size of 1,000 games, quotation mark small, you can see the shape of the bell curve come in. But if you increase the number of runs to something much larger, you can see it start to approach a better binomial distribution, which I will show you now. Okay, so this is what the curve looks like when it's 1,000 games. You see it's a bit jaggedy and it's not really as perfect as the binomial distribution from this file. Let's give it a run just so we can compare it side by side. It doesn't take that long to run, which is nice. So yeah, as you can see, this is a lot smoother. So this is kind of what it will look like if you have an infinite number of games to sample from. But let's increase the sample size to see what the difference is. So I'm going to increase it to 10,000 right now instead of 1,000 and let it run. Okay, so it finished the simulation of 10,000 runs. As you can see, it took a lot longer, but it's approaching a more perfect bell curve, similar to that from the binomial distribution. But yeah, so out of 10,000 games, this is where for its game would sit. Hi, Expert from the future again, and just to mention that is the distribution for the looking for the word T-gun specifically, not the distribution of his whole game of all the 3 guns combined. But it's not important which gun it's looking for because the distribution is the same for all of the guns in the game. It's more important the amount of hits there is in one game, and the shape of the curve depends on how many times you run that game. But yeah, I will explain later why this amount of hits in one game is important. It shows the same thing as the binomial distribution. So that's sort of the purpose of this box histogram.py. It shows almost the same thing as the binomial distribution. Let me put them side by side again. So if you have the binomial distribution side by side with the box histogram, you will see that the y-axis is slightly different because this is occurrence, is how often each one of these lucks has occurred out of 10,000 games. But for this is the probability. It shows basically the same thing. You can see comparatively how common the different bins are, but the x-axis is the same, so that's why I'm referring to as bins. But yeah, that's how you simulate 10,000 games or whatever number you want to put in here. The larger the number you put in, the longer it's going to run for, because it has to simulate all the games, and Python isn't the fastest language out there, so it takes a while. One other thing I forgot to mention is that for all of these files, you don't really need to worry about what's happening here, unless you want to also start messing around with it. Worry more what's happening down here, because this is where you input the numbers into the sim, and then it just generates them from what you put here. But also, on the topic of the histogram, I have another file which does the same thing, but it shows it to you animated. So it generates the random games and it puts them in a bin, but you can see it happen live as it goes through simulations. It's a bit slower, quite a bit slower than the other one, but it kind of helps you visualize how the occurrences pop up. As you can see, for the numbers I've put in here for 2,500 and it goes up to 1,000 simulations, you can see the curves start to develop here around 125 successes. I'm not sure if that's 0.05. Let's see. Is that 0.05 of 2,500? Yeah, look at that. Boom. quick maths. But yeah, the more you watch this, the more it's gonna look like a curve, bell curve centered around 125. And yeah, it's quite slow, which I can't be asked to dig through the matplotlib code to figure out how to optimize it, but I guess you can stare and be mesmerized by the little growing mound of successes. I'd probably stick to using boxhistogram.py as it's much quicker though, unless you just want to be mesmerized. Okay, so once you're done being mesmerized by the animated histogram, feel free to join me in the second part of the simulations part of the video, which I think is like part 4 now or whatever, I don't know. But yeah, in this part of the video I show you some interesting observations of how the box works. So imagine that you run one game. Let me quickly screenshot this. And for this game you put a green color on the most common gun, if I can get the brush. So you put a green dot for the most common gun, a blue dot for the least common gun, and a red dot. Well, that's not. I need a blue dot, not a green dot. There we go. And a red dot for the gun that you're targeting. So let's say we're targeting the T-gun, so a red dot here. And then I move on to the next game and I do the same thing. So let me run it again. So I have another simulation. Let's get that. Put it in paint and then do the same thing. Red dot for the T-gun, green dot for the F, my favorite gun, and a blue dot for dolls. Dolls are the least common here. And you plot all of these on a graph in terms of how often they came up. So if you make a trade ratio out of this, so it will be the total number of box sets divided by this number. So if you repeat this step a couple hundred times and put it on a graph, you get something like this. So on the y-axis is the trade ratios, which is the number of box sets divided by the amount of times that gun appeared. And on the x-axis is just the steps. So each slice to the right is a different simulation, and there's 200 of them like this. On each slice, you will see a blue dot, a red dot, and a green dot. And as I stated previously, green is the most common, blue is the least common, and red is just the gun you're targeting. Also, here you can see that sometimes there's a red dot with a green dot, and what this means is that it's the most common gun of that game, or in the top 2, or something like that. And sometimes you see a red dot with the blue dots, which means it's the least common gun of that game, or in the top 5 least common guns. And yeah, another interesting thing that you can observe is that you see that the most common guns range between about 2 trade ratios, from 18 to 16 and a little bit below. The gun you're targeting ranges from like 18 to 23, and the mass of it's there. So that's a wider range than the most common gun. And the blue guns, the least common guns, are even wider, and you're more likely to be to get very unlucky than to get very lucky, it seems. So if you do the same graph and you just increase the number of games or the number of steps to a lot more, we'll find something interesting. So let me put down to 2000 games instead of 200. So as you can see here, with the higher sample size, the line is kind of straightened out, and we can see everything I said in the previous graph is reinforced. And it's not that common that you'd see a red gun, the gun you're targeting, go below this black line, which is the 16.55. The most common gun of the game does go below that number, and it's quite common that the most common gun of the game will. However, the T-gun, or any random gun that you target, is not as common. It's about 1 in 76, which happens to coincide with this. But the more you run it, the more accurate it's gonna be. This is just a coincidence that it's exactly 1 in 76. Nice for the demo, right? And yeah, another thing about the script is that it prints out information in the console whenever the game is better than the target value that you put in, the target trade ratio. And I'm just showing you another example. It's not always going to be 1 in 76 with such a small sample size. That was just a coincidence. The bigger the sample size, however, the better it is. And also the reason I'm kind of refilming this is because I had to change a little bit in the code, because this did not print at the end of the script. It was only printing while it's running. So now it'll give us a nice little print at the end. Oh yeah, if I didn't already mention, whenever a game has a T-gun that has a trade ratio better than 16.5, it just appends 1 onto the count and then tells you the information about the game. So as you see, after 20,000 runs of a game of 2, 3, 6, 7 box hits, we get a 1 in 72 chance, which isn't that far off. So another way you could use this code is if you use this increment box hit argument for the function, and if I set that to 1, that means that every time the simulation goes one step further, it will add 1 to the box hits. So let's start off at a relatively low number, and let's make it run for 4,000 times. So it will start off on 300 box hits, and then the next one will be 301, and then 302, and to still collect the data of the least common, most common, and the target gun. So in this case, T-gun. So here it is, and isn't that interesting? So at around 300 box hits, because it starts off with 300, you can see that you're very likely to get much more crazier bad luck, quotation marks, for the least common gun. And you can see a lot of red dots here in the least common gun range. And you can see a lot more red dots here in the most common gun range as well. So you're a lot likely to get a trade ratio lower than 16.55 at 300 box hits. But as you see, as it progresses, as the games get more and more box hits in them, the distribution starts to tighten and you get less luckier or less likely to get very lucky because you have a larger sample size, so there's less spurious deviation from the median, from the norm. And as you can see from the point of about 2000, which is where about 2300 is, not a lot of times does the red dot happen below the 16.55. And also there's a lot of red dots here in the generally meh luck, like the 25 trade ratio. And there's quite a few here as well, but there's less. Like they're all above this 16.55. So it's generally lucky that you'd see a red dot below 16.55. This is just to visualize the data. You can zoom in on different regions if you want with this as well, if you really want to observe. Zoom in and inspect. I don't know, I've never clicked these things really. So yeah, you can go back as well to the original graph. But yeah, I just thought that was fascinating, the way that you can see how your luck just becomes less likely to be lucky the longer your game is. Also, this is another way that you can see that's kind of interesting, that if you run it, you can see at the beginning, it just prints a lot of them very quickly, but then when it gets to about 2,300 box hits or later, it becomes a lot rarer for a gun to be below 16.55. And yeah, I just thought this was really fascinating, and it kind of explains to people like MC who likes to send me pictures of people's games, and they're like, oh look, he has 600 box hits, look at his box luck, he's cheating. No, you're just at 600 box hits, you're just quite likely to be very lucky and very unlucky at the same time. Look at this. I think this is like 600 right here. I don't know why I zoom in, it's harder to look at it, but yeah, that's 600. There's a lot below 16.55, and there's a lot up here. So yeah, watch out, MC. So yeah, that was the boxluck example.py. Probably not the best named file. I might be changing that in the future. You saw me change the code as I'm recording this, so do expect to find some changes. However, I will document them in the README or somewhere. It'll be obvious. But yeah, there is one more script which is a bit far-fetched, but I'll try to put into perspective what I'm talking about. So it's sort of a roundabout way of finding the probability that you get the luck that you have gotten for the T-gun Gersh and those or better at the same time, because all of the previous scripts has been showing the chance of getting one gun isolated from the other two. So since it's a bit difficult to emulate this because of the varying sample sizes, and by that I mean that the Gersh has a lot less of a sample size than the dolls and the T-gun, and that's important because remember from that diminishing graph it showed that the less sample size you have, the more likely you are to be lucky. So in order to try to account for the higher luck that you get from lower amount of box hits, I have made it run 3 different games, one for the T-gun, one for the Gersh, and one for the dolls, and each one of them looks for the particular gun in question, and each one of them runs for the given amount of trials for its game. Here, at the top of the file I defined it here. And it will then look at the probability of the 3 guns and to compare them to the probabilities that you put in here. So I have a T-gun, a Gersh, and a dose probability. These 3 probabilities are the probabilities of Furret's guns. So if we look at the sheet real quick, it's these 3 here. So 0.013, 0.042, and 0.012. I've just copy and pasted them. And if they happen to, all 3 of them, be better than these probabilities, it will then increment by 1 and it will print something in chat. And by better than, it compares each respective gun to this probability. So it compares the T-gun to Furret's T-gun, the Gersh to Furret's Gersh, and the dolls to Furret's dolls. And this will keep running for whatever number you put up here. And this probability is the probability of getting a gun. So 1 in 20, 0.05. So this takes a bit of time. It's a bit longer than the other sims because it does free game simulations. So I'm just gonna run it once till 150,000 and see if it will happen at least once. If at least once we'll get a game as lucky as Furret's game. But keep in mind the disclaimer that this is 3 separate games. So it isn't exactly analogous as getting them all from the same game. But you can have some liberties here, make the assumption because it is an independent probability, it's the same as it being from 3 different games. But then again, that's up to you to interpret. So yeah, that's one thing I can improve in the future about this script, but if I can create a more true to the game simulation, which when the player has a state of what they have in their hands, so it will track if you have the T-gun dolls in your hands, which drops you have, and when you trade out, and then the probability of getting the 3 guns from the same game will be a bit more accurate rather than 3 different games to get from different trials. But yeah, that's just more dev work for me in the future. If you guys really want me to do that, I can. I decided to work a bit more on how the logic of this works, so this part of the video is a little bit anachronistic, but I also let it run overnight for like 8 hours or something like that, from like 12 AM to 8 AM, and out of 2.5 million games, it could find only 13 games luckier than Furret's game, equal to or luckier than Furret's game. So this kind of reinforces the luck we found by multiplying them together. As you can see, it's actually even luckier out of the 13. It's not a big enough sample size. I need to run this for like a billion times or something like that. But this kind of shows that it is very lucky to get the 3 lucks combined. So yeah, this script might be the most fun to play around with. So to conclude, I hope I've explained or at least helped give some depth to what the numbers mentioned in Crupp's video mean, and I hope this helps you interpret it. I'm not going to make huge statements on if Furret or anyone's game is legit or not. It may be sus to me, but it's up to you to decide what is sus, and I hope I've equipped you with the right tools and knowledge for that. I hope this has cleared up any questions that may have been raised by Crupp's video about this. If you have any questions, please do comment them down below or tweet them at me. Hopefully instructions on how to use my Python files was also clear, and I will continue to update the repo should I think of new ideas or anyone has any suggestions. Also, I really hope that I've helped at least one person learn something from this video about statistics and math, and I hope I've inspired someone to get into statistics or programming or something like that. That would be the best case scenario for me. And also, make sure you look at the description. I've left a few further reading things if you really want to learn more about this. And also, watch Matt Parker's video. He's really good. That's the stand-up maths guy at the beginning of the video that I mentioned, by the way. But yeah, until the next time I'm dragged out of the shadows for another video like this. Bye bye.
Hey, Strange! You know what's cooler than magic? Math!